Started. Okay, hello, everyone. My name is John Lee. Welcome to Major Savings with App Startup Shavings. Whew. So I really enjoy app performance programming because of this one single memory where I had the opportunity to decrease the TTI, or time to interactive, of our first screen in the Wayfair app from 5.9 seconds to 1.88 seconds. So that's a 69% decrease through caching and lazy deferral. And in that moment, I felt so proud because I made such a big contribution that I can see, that I can measure with numbers, and there was so much joy in that. It was a really great moment for me. And that's one of the reasons I want to give this talk. I wanted to show some of the techniques and patterns so that all of you can have a moment like this. So let's start off with the basics. What is App Startup? First, there's really 4 steps. One is your app process initializes. The next thing that happens is the content providers in your Android manifests, they get a chance to initialize. After all that's done, then your application initializes. Your application on create, and then your activity initializes. So 4 steps. Why should we care about App Startup? So there's a really famous story of Amazon. They did a study where every 100 milliseconds added to a page load time, they lost 1% in revenue. That's a really strong incentive to make sure your pages load fast. Another thing is users like fast experiences. They're more likely to be engaged for longer. And another thing, App Store ranking. So there's a set of metrics given by something called Android Vitals. One of them is App Startup speed. And if you have poor App Startup performance, you will have lower App Store ranking. So users may not even see your app or discover your app if your App Startup is slow. So how do we figure out where we need to go? Do we have some kind of guidance? And we do. Google, through their documentation, gives us 3 thresholds. Cold startups should be less than 5 seconds, warm startups should be less than 2 seconds, and hot startups should be less than 1.5 seconds. Okay, so with all of this out of the way, we can talk about the first category of techniques we're going to go over, deferral patterns. The idea of deferral patterns is basically doing work closer to where it needs to be done, not earlier, not before. And we can look at an example of a feature flag repository. Basically tells us which A/B test flags are active or inactive. And this is backed by shared preferences, right? Okay, so one thing about initializing this class, when you instantiate it, you actually also instantiate shared preferences. So the creation of the repository class is coupled with the creation of the shared preferences. And that may not be the most ideal thing, because you may have a case where I'm going to create this class, or Dagger or whoever may create this class, but I'm actually not going to reference or use shared preferences yet. That might be maybe further into the app. So you don't want these 2 things to be coupled. So part of the deferral pattern is decoupling these 2 things. And one good way of doing that is the lazy delegate. It's like 1-2 lines of code, very simple to do. And I recommend potentially adding this or initializing your properties by lazy delegation to decouple that work from the instantiation. Now, shared preferences can be expensive because let's say you have a lot of entries in shared preferences. Let's say you have large entries in your shared preferences. Those are the reasons why you don't want these things to be tied together. Okay, let's see. Let's talk about another example in the realm of lazy. We have an address repository. It has these 4 dependencies. We're using Dagger. How do we do lazy here? Very simple. We just add the lazy tag. Most dependency injection frameworks have this concept. And when we apply these lazy tags, we're able to basically instantiate all of these dependencies without running the initialization code until it's actually used, which is pretty great. Let's see. Okay, so here's an advanced pattern. Deferring features using the dynamic feature module. Surprisingly, it's not a lot of code. So let's look at it. Let's say we have an app around people that love broccoli, and they post pictures of their broccoli dishes, and they have a feed of broccoli reviews. And you have a map where people can look for broccoli dishes at restaurants. So you have a feed, you have a map. Let's look at that visually. This might be your module structure. You have an application module, you have a feed module, and you have a maps module. And we expanded out the maps module, so it's like feature, library, and then you have an expensive third-party library that you use to fulfill all of this stuff. And let's say in this app, people don't really use the map feature, but people really love the main feed feature. So is there a way we can approach making startup faster for the majority of users? And that's where we get into dynamic feature modules. So the first thing we do is we create a dynamic feature module in between the application and our feature. And to get started, you basically go to Android Studio, File, Create New Module. You select Dynamic Feature Module, and it'll basically create most of the setup for you. Let's look at some of the changes it does. In your app build Gradle, it adds this entry. But also in your app Gradle, you can remove the dependency to that feature module because you don't need it during the app startup. It's actually going to be installed post-runtime and post-installation. So the next change is your new dynamic map module. It will look something like this. It's going to have a dependency on the app module, and you're going to add your dependency on the feature module. And the last thing, I want to install this module during runtime. It could be after app startup. It could be in the background. This is essentially all the code it takes to install that module. You have the split install manager. You create the request. You have the callback to if it's successful or not, and then you're able to navigate to that feature afterwards. Before we get into this new category of parallel performance patterns, I want to give an example of why we want to defer code. And this example comes from 2 weeks ago, where I opened up my email, and I see this email telling me this is a huge spike in background ANRs. And so I go and look at the stack trace. It's telling me that this ad service is creating web views on the main thread during app startup. So I dive into the documentation. And basically, we turned on this flag to pre-cache ads. So what that does is it'll create a group of web views inside this third-party library. And that's probably not what we want to do in app startup. We probably don't want to spend main thread time doing that because app startup time is precious. We want to defer that work closer to where ads are shown. So that's just a great example of like why sometimes we can move work further ahead rather than be in this important space. So the next category is parallel performance patterns. And let's go back to our feature flag repository. How can we parallelize this? Well, one very simple way is make it late initialize, and in the actual constructor block, init block, we can initialize it inside a coroutine scope. And for this example, let's say we have an extra method, is flag active, we get the Boolean, this is part of the class, and it will explain the next part. What happens when we run this code? I'll give it a second. I do hear a lot of people saying it's going to crash, and that's actually correct. It'll say uninitialized property exception. So we have a race condition. This is a common occurrence called a race condition. And why does this happen? Let's look at the code again. In our init block, it schedules work to initialize the shared preferences, but it doesn't guarantee that's going to happen immediately. And the core of this issue is we are combining synchronous and asynchronous concerns in a single flow. That's a problem. One of my favorite ways to resolve this is actually to make the entire API asynchronous, so you can avoid race conditions. And one super simple way to do that is using coroutines. But before we go in coroutines, let's add this hack back in. We're going to lazy initialize it, just like we learned from a few slides ago. So if we were to use coroutines to remove the race conditions, we would update the isFlagActive method to be a suspended method. We can even define the thread pool that it will run in, and that will actually solve a race condition. Not a lot of code. And this is what the execution code would look like. Another way to approach this is using flows. Very similar concept. Instead of using a suspended method, you return a flow of a Boolean, and you emit the actual result. And the execution code looks like this. All pretty simple. And if we were to visualize this, where the green thread or the green background is the main thread, the orange background is our background thread. So the feature flag repository gets instantiated, the repository isFlagActive gets called, and then the main thread continues. It's not blocked. And at some point, our scheduled work, the isFlagActive, that gets called. Since our shared preferences hasn't been initialized yet, thanks to lazy, and this is the first time we're calling it, it will be initialized on that thread, and then it calls getBoolean. So the next pattern I want to talk about is one I like to call divide and conquer. Very commonly in app startup, you're going to initialize a bunch of things. In this example, let's say we have a logger class, we have AddMob SDK, we have our OKHTTP component, Room Database, Google Maps, right? None of these have dependencies on each other, and commonly, they probably don't have dependencies at all with anything else. So if we were to initialize it, it may look something like this. And let's say I added hypothetical durations to each of the initializations. It would be about 1,600 milliseconds if I were to do this sequentially on the main thread. But we can do better. I say we can do something like this, where we parallelize them all at once in parallel. And I can get the time from 1,600 milliseconds to 500 milliseconds. How can we do this? Well, good thing we have Kotlin to help us out. This is essentially all the code that you'll need to make that happen. And we'll break it down. Let's look at Parallel Initializer first. It's basically a factory class where you have a create method, and then the result delegate basically outputs the callback of the results of the initialization. Just two responsibilities. OK, so let's look at the code itself. This is an extension method for a list of parallel initializers. We call parallel init, pass in the context. That's the function signature. Let's go through this line by line to simplify things. Run blocking means we'll run the main thread, hypothetically the main thread. Map is our for each, so for each initializer. Schedule some work on this thread pool. Inside this asynchronous thread, initialize the whatever you're initializing. And the key to do all of this, await all. Block until all of these initializers are done. done from their work on separate threads. And this is the recap of all the steps. And that is how we achieve this. And there's a lot of opportunities here because we initialize a bunch of SDKs. We have a lot of like zero dependency components. We can do a lot of that work with something like this. And good thing we have Kotlin to help us out to make this simple. So if we were to take our existing example, this is what the code would look like in execution. We make a parallel initializer for logger, add mob, etc. And we have a callback if we want to collect the result, like we want to have an instance of the OKHTTP client or the database. Okay. Next up, we have the Jetpack app startup library. And I'm going to have to explain this before I talk about something super advanced. So this library is actually small, very simple. It introduces a basic initializing component, and through having implementations of that component, the library can intelligently sequence and order which component should be initialized first based on the dependencies. So let's look at the initializer. Like I said, very simple. Create method, and then you have a list of dependencies. So when we look at an example of this, I can initialize a room database using this interface. It'll look like this. Very standard room database initialization code. And for dependencies, well, normally databases don't have dependencies, so we return an empty list. And all the patterns I introduced in this talk can only be applied after application onCreate. And potentially in the activity, right? But what if there's a pattern or technique we can do to optimize the content provider step? Well, there is, using this library. And this was actually first introduced by Chet Haas in a 2-part article that'll be referenced in the slide at the end, where the goal was to defer the work manager content provider to initialize later so it doesn't take up time before application onCreate. So let's look at how that happens. How can we basically defer a content provider and move that initialization to post-startup? Well, first, we will remove the content provider. So tools node remove is kind of the main key of this. You remove whatever content provider that you're trying to initialize later. Next, you create the initializer using the initializer interface provided by the startup library. So this code is the exact code that the content provider invokes. So they have to be very similar. Work manager has no dependencies, so you create this initializer. You let the initialization provider, which is a content provider provided by the app startup library, know about this initializer. Once it knows about this initializer, it can automatically initialize it, you can manually initialize it, but enables the visibility of it. And last thing to do is actually initialize it during runtime. You can do this in some activity, you can do it post app startup, you can do it during startup, up to you. And an optional step, initialize it asynchronously. So here are all the steps. Again, you remove the content provider from the manifest. You create a new initializer to replace the content provider. You copy and paste the initialization code into your initializer, and then you actually call the initializing code. OK. So closing thoughts. What are my closing thoughts? So here are a bunch of patterns and ways to draw inspiration from when you look at performance challenges, because performance challenges are an entire category of problems, not single problems. And that's why it's important to have a lot of tools in your tool belt to know more about these techniques. And hopefully, I hope all of you walk out of here having a few more of those tools and experience some of the joy of app performance programming that I have. Thank you.